prove an interesting property of the real numbers based on the least upper bound property of the real numbers. Now, this is the definition of least upper bound down here of any ordered set. And the ordered set we're dealing with is R, the real numbers tonight. But this value right here, the supremum, that is the smallest of all the upper bounds. Okay, this stands for supremum. I've seen it called just LUB, least upper bound. Okay, least upper bound. LUB, lub, least upper bound. But in any event, that comes in handy in proving this fairly obvious looking result here. This says that if you have any pair of real numbers where one of them is positive, there's a natural number such that when you multiply the positive number by that natural number, you're going to get this inequality. Now that seems stone cold obvious, but you actually need this least upper bound property. Okay. Now what we're going to do is we're going to consider this set, because if you look at this, this is an integer, a positive integer multiplied against a real number, and so we're actually listing all multiples of all positive integer multiples of x right here. This is called set builder notation. I think when Rudin proved this, he just says let I run through all the positive integers. I like this set builder notation a little bit better. Now notice this is not empty, obviously. It's not, it actually contains values, which is nice because that's part of the statement here. E cannot be empty, which is clear. I don't even know why they mention this a lot of the times. Okay, but what we do it's kind of a classical proof by contradiction. We suppose that what we're setting out to prove is actually false. Now notice we have this existential quantifier here. It says there exist. Well, the negation of this existential quantifier is this universal quantifier right here. So notice how we just reverse the order of the inequality. We say that y is greater than or equal to nx for all natural numbers. So what does that mean? That means, well, we have the bounded above now, okay? E is bounded above, okay? It's bounded above by this y right here. So that's kind of nice. So we have that condition met, all right? And again, this is just a reclarification. Y is an upper bound for this set, okay? Which is exactly what this LUB property is talking about down here, okay? Now, so that means it's going to have a least upper bound. We're going to call it U, and that would be this right here. In other words, this would be the LUB right here, or the supremum. Sometimes they call it the supremum, LUB. Okay, but in any event, because it's bounded above, it has a least upper bound. That's a property that the real numbers possess by construction. Okay, so what that means is that U minus X is not an upper bound. Let me write this down right up here. U minus X. And that's because X is positive, right? U minus X, not an upper bound. I'll just call it a UB, folks, an upper bound. You allow me to abbreviate that, folks. UB stands for upper bound. Okay. Now, since it's not an upper bound, it's back in the original set. Since it's not an upper bound for the set, it has to be contained in this set, which is what this statement says right here. U minus X is not an upper bound, therefore it can't be outside the set, it has to be in the set, all right? And so this is just another way of stating it. It's going to, U minus X has to be less than or equal to some integer multiple of X contained in this set, of course, all right? Now, if you do the algebra here, if you add X to both sides, you get this statement right here, which is a very clear contradiction, right? It's a very clear contradiction. It's saying that the least upper bound, this least upper bound U, is actually less than a member of the set, which is a clear contradiction. So what did we contradict? We contradicted that this was false, and so that means it's true, right? So we've actually shown that nx, there exists an nx, there exists an n such that nx is greater than y. Okay, again, we got a contradiction when we assumed that what we were trying to prove is false. Okay, so I guess we can write QED here, folks. And I liked it a lot. The rational numbers don't enjoy this property, but the real numbers fill in the gaps, so to speak, of the rational numbers. And you need the LUB property to prove something that, I mean, like I say, this just seems dead obvious, but it does require some proof. And I wouldn't call the proof trivial. A little bit of work here. But anyway, it's kind of a connection between the order of the real numbers and set theory, the way I look at it. Anyway, I hope you enjoyed.